Welcome back to Snooze to Astronomy. Tonight we will take you through a long and restful journey through 155 facts about supernovas. So sit back, close your eyes, and enjoy the video. A supernova is the violent death of a star. An explosion so bright it can outshine an entire galaxy for days or weeks. During this brief moment, a single star releases as much energy as the sun will in its entire lifetime, flooding the cosmos with light and matter. There are two main types of supernova. Type I happens when a white dwarf in a binary system steals matter from its companion star until it collapses and detonates. Type II occurs when a massive star, at least 8 times the sun's mass, burns through its fuel and its core implodes, causing an outward shockwave. Supernovae are essential to existence itself. Heavy elements like iron, nickel, and gold are forged in their fiery deaths and scattered across the universe. Without them, planets, oceans, and even human blood, rich with iron, could not exist. We are literally made of star remnants. The shockwaves from supernova race outward at thousands of kilometers per second, compressing nearby gas and dust. This compression can trigger the birth of new stars, making supernova both an ending and a beginning in the grand cycle of the cosmos. One of the most famous supernova remnants is the Crab Nebula, born from an explosion observed in 1054 AD. Chinese and Middle Eastern. Astronomers recorded a guest star so bright it was visible in the daytime for weeks. Today, its expanding filaments stretch across space in a dazzling display. Supernovae are rare in a human lifetime. In a galaxy like the Milky Way, one occurs roughly every 50 years. Yet because galaxies number in the trillions, astronomers using telescopes can witness new supernova every night somewhere in the universe. When a massive star dies in a core-collapse supernova, its heart may collapse into a neutron star, an object so dense a teaspoon of its material would weigh billions of tons. If the progenitor star is even more massive, the collapse may form a black hole. Type Ia supernovae are so consistent in brightness that astronomers use them as standard candles to measure cosmic distances. By comparing their apparent brightness with their intrinsic luminosity, scientists map galaxies across billions of light-years. The discovery of type Ia supernova in the late 1990s revealed something astonishing. The universe is not just expanding, but accelerating. This led to the idea of dark energy, a mysterious force that pushes the cosmos apart and dominates its fate. Some stars die in spectacular fashion known as hypernovae explosions, even more powerful than typical supernova, possibly linked to the birth of black holes and gamma-ray bursts. These outbursts release jets of energy across unimaginable distances. Gamma-ray bursts, the most energetic events known, may originate from collapsing stars undergoing hypernova explosions. For a few seconds, they can release more energy than the sun will emit in its 10 billion-year life, sending deadly radiation across space. In 1987, a star in the Large Magellanic Cloud, a neighboring galaxy, exploded as supernova 1987A. It was the brightest seen in over 400 years and provided astronomers with a rare opportunity to study the process in detail with modern instruments. SN 1987A revealed rings of glowing material around the star, ejected before the explosion. Over decades, astronomers watched these rings brighten as the shockwave struck them, providing a living laboratory of stellar death. Some supernova produce pulsars, rapidly spinning neutron stars that beam radiation like cosmic lighthouses. The Crab pulsar, born from the 1054 supernova, spins 30 times per second, emitting pulses of energy we detect on Earth. The energy of a supernova is so intense it can sterilize nearby planets. If a star within 30 light-years of Earth were to explode, its radiation could damage Earth's ozone layer and alter life drastically. Luckily, no known nearby stars pose such a risk in the near future. Betelgeuse, the red supergiant in Orion, is a candidate for a future supernova. It has swelled to enormous size and nears the end of its life. When it explodes, it will shine brighter than the full moon, visible in the daytime. Though it lies safely 642 light-years away, supernovae not only enrich galaxies with elements, but also stir interstellar gas, preventing it from collapsing all at once. They act as cosmic gardeners, pruning and fertilizing, shaping the growth of galaxies across eons. The shockwaves of supernova create cosmic rays, high-energy particles that travel through the galaxy at nearly the speed of light. Some of these particles strike Earth, influencing atmospheric chemistry and possibly even affecting evolution. In the early universe, the first stars, called population 3 stars, were massive and their supernova seeded the pristine cosmos with the first heavy elements, paving the way for later generations of stars, planets, and life. Astronomers sometimes witness superluminous supernova explosions, dozens of times brighter than normal. These rare events may result from stars with extreme magnetic fields or from collisions with dense circumstellar material. Some supernovae are asymmetric, spewing material in jets instead of spherical shells. These lopsided explosions may explain how neutron stars get kicks, moving through space at hundreds of kilometers per second. Supernova remnants remain visible for tens of thousands of years, expanding into colorful nebulae. These remnants become laboratories for studying shockwaves, magnetic fields, and the chemical fingerprints of stellar death. The light from supernova can echo off interstellar dust, producing light echoes years after the explosion. Astronomers use these reflections to study the original event, long after the star has vanished. Supernova enrich the interstellar medium with carbon, oxygen, silicon, and other elements. These elements later condense into new solar systems, ensuring that future worlds inherit the ashes of ancient stars. In 1604, a supernova appeared so bright it rivaled Venus, known as Kepler's supernova. It was the last naked-eye supernova observed in our galaxy. Its remnant is still studied today with X-ray telescopes. Tycho Brahe recorded another famous supernova in 1572, shaking the belief that the heavens were unchanging. His careful observations helped spark the scientific revolution and a new understanding of the cosmos. Supernova can occur in galaxies billions of light-years away, their light traveling across time to reach us. Each one is not just an explosion, but a message from the deep past, telling the story of stars that died long before Earth even existed. Some supernova leave behind black holes that continue to feed on their surroundings, creating X-ray binaries. These systems allow astronomers to study black holes indirectly by watching how they devour nearby matter. Supernova, neutrinos, are tiny, ghostly particles that stream out of collapsing stars in staggering numbers. In 1987, detectors on Earth caught neutrinos from SN 1987A, giving direct evidence of core collapse physics. Some supernovae shine brighter than their host galaxies, briefly becoming the most luminous object in the universe visible from that location. This overwhelming brightness has allowed astronomers throughout history to spot them without telescopes. Even in the daytime sky, when a supernova detonates, shockwaves slam into surrounding gas clouds, heating them to millions of degrees. This interaction lights up the nebula in X-rays, giving astronomers clues about the density and structure of the interstellar medium. Supernovae are key to galactic recycling. Without them, galaxies would lose energy, and metals would stay locked inside stars. By blasting materials outward, they maintain the cosmic ecosystem that makes complex chemistry and ultimately life possible. Some stars don't explode all at once, but undergo multiple outbursts. These are called supernova impulses, where a massive star erupts violently but survives, only to collapse in a later, final explosion. Eta Carini, a famous luminous blue variable, may be such a candidate. Supernova explosions enrich the cosmos with radioactive isotopes. Some of these, like aluminum-26, have been found in meteorites from the early solar system, proving that nearby supernova seeded our planetary nursery. Astronomers can sometimes identify the exact progenitor star of a supernova by examining archived telescope images. Seeing the star before and after its explosion offers direct insight into which types of stars produce which supernova. The term supernova was coined in the 1930s by Walter Baade and Fritz Suzuki. They realized these were not just novas, but a fundamentally different phenomenon, the catastrophic destruction of stars, leading to neutron stars and black holes. Some supernova are so faint they were missed for centuries, but modern infrared and radio telescopes reveal their remnants. This shows the Milky Way has hosted many more stellar deaths than written human records suggest. SN 1054, which created the Crab Nebula, was so bright it was visible in daylight for nearly a month. Chinese court astronomers meticulously documented its appearance, leaving a treasure trove of records for modern astrophysicists. Supernova remnants expand at supersonic speeds, creating shock fronts that heat gas and accelerate particles. These shock fronts are natural laboratories for plasma physics, conditions impossible to recreate on Earth. In dwarf galaxies, which are small and faint, a single supernova can drastically change the entire system by blowing out gas and halting star formation for millions of years. In this way, one star's death can reshape whole galaxies. Some of the earliest clues about cosmic expansion came from supernova studies. Because their brightness is consistent, astronomers use them to chart the distances to galaxies, building the foundation for modern cosmology. When the core of a massive star collapses, it squeezes protons and electrons into neutrons, releasing a flood of neutrinos. In just 10 seconds, more neutrinos escape than the Sun will emit in 10 billion years. Astronomers sometimes detect supernova shock breakout, the exact moment a star's surface is blasted apart. For a few minutes, 2 hours, a burst of ultraviolet and X-ray radiation signals the star's last breath before its light fully blooms. Not all massive stars explode. Some may collapse directly into black holes without producing a visible supernova, vanishing silently from the night sky. A cosmic failed supernova. Detecting these disappearances is an active area of research. The remains of supernova often mix with interstellar dust to create complex molecules. Astronomers have even found amino acid precursors in these environments, hinting at a link between stellar deaths and the ingredients of life. Supernova are categorized by their spectra, the light they emit. Type 1 lack hydrogen lines, while Type 2 show them. Subclasses break down further based on helium or silicon features, revealing the composition of the progenitor star. A single supernova can eject several solar masses of material into space, hurling it at thousands of kilometers per second. This debris becomes part of the next generation of stars and planets, seeding the galaxy with richness. Because supernova are so bright, they act as beacons to study intergalactic dust. By watching how their light dims and reddens, astronomers can map the distribution of dust between galaxies. The Cassiopeia, a supernova remnant, is about 11,000 light-years away and exploded roughly 350 years ago. It remains one of the best-studied remnants, glowing in radio, infrared, and X-rays, showing scientists how shockwaves shape interstellar gas. Some supernovae show evidence of interaction with companion stars. In these cases, the blast strips material off the companion or heats it, leaving a signature in the explosion's afterglow that astronomers can detect. The heaviest elements, like uranium and gold, are created in the extreme conditions of supernova and neutron star mergers. Every wedding ring and computer circuit traces its atoms back to stellar death throes. Not all stars that die as supernova are giant, white dwarfs, the size of Earth, but with the mass of the Sun, can also explode when they accrete enough matter from a companion star to exceed a critical mass, the Chandrasekhar limit of about 1.4 solar masses. The light curves of supernova, how their brightness rises and fades, are studied in detail. These curves reveal the type of explosion, the mass of material ejected, and the presence of radioactive isotopes like nickel-56 that power the glow. Supernova remnants are cosmic particle accelerators. They propel particles to energies far higher than man-made accelerators like the Large Hadron Collider, showering the galaxy with cosmic rays. Astronomers studying supernova remnants in X-rays have discovered knots and clumps of material that move at different speeds. This turbulence shows that explosions are messy, chaotic events rather than perfectly symmetrical. SN 1006 was the brightest stellar explosion recorded in history. Visible worldwide in 1006 AD, descriptions from China, Japan, Europe, and the Middle East speak of a guest star so brilliant it casts shadows at night. Supernova have inspired human imagination as omens and wonders. In ancient times, they were seen as signs from gods or harbingers of change, their sudden brilliance disrupting the predictable cycles of the sky. Some galaxies, called starburst galaxies, produce stars so rapidly that they also host frequent supernova. These explosions enrich the galaxy quickly, creating a cycle of birth and death, far more dramatic than in the Milky Way. Supernova light can take thousands or millions of years to reach Earth. By the time we see an explosion, the star has long been gone, and its remnant has already begun evolving unseen across space. Astronomers use computer simulations to model supernova explosions, but even today, the exact mechanisms of how shockwaves propagate and stars collapse remain some of astrophysics' most challenging problems. The violence of a supernova is so extreme that it can twist magnetic fields on cosmic scales. These fields, amplified by turbulence, shape the structure of the resulting nebula and influence cosmic ray acceleration. Supernova remnants glow in every wavelength of light: radio, visible, X-ray, and gamma-ray. By combining data from multiple observatories, scientists can piece together a multi-dimensional picture of how the explosion unfolded. The universe's expansion rate, the Hubble constant, has been measured using supernova as distance markers, but recent measurements show a tension with other methods, hinting at new physics or unknown cosmic components. Supernova can occur in binary systems where massive stars orbit one another. In some cases, both stars explode within a few million years, creating overlapping remnants and enriching their surroundings with extraordinary amounts of material. The elemental composition of the human body: iron in blood, calcium in bones, oxygen we breathe, was forged in supernova. Every person is a living testament to these cosmic explosions. In rare cases, supernova can briefly create neutron stars with magnetic fields trillions of times stronger than Earth's. These exotic remnants can unleash giant flares that dwarf the brightness of their progenitor stars. Explosion. Astronomers sometimes find supernova twins, pairs of nearly identical explosions that happen in different galaxies. Studying these allows for precise comparisons of cosmic conditions across vast distances. The study of supernova spans disciplines from nuclear physics to cosmology. Understanding them requires knowledge of quantum mechanics in collapsing cores, chemistry of dust grains, and relativity for black hole formation. Some supernova leave behind expanding shells of polarized light, which tells scientists about the geometry of the explosion. This polarization shows that the blasts are often not perfectly spherical but distorted and complex. Supernova explosions release gravitational waves, ripples in spacetime, though detecting them is extremely difficult. Future observatories may one day listen to the death cries of stars through these cosmic vibrations. The brightest known supernova, SN 2006 GY, was more than 100 times brighter than a typical event. It may have been caused by a pair instability supernova, where matter and antimatter annihilate inside a massive star, driving it to explode completely. Supernova can dramatically alter their galaxy's appearance. Shockwaves carve bubbles and cavities in the interstellar medium, producing vast structures known as superbubbles that stretch for hundreds of light-years. The timing of nearby supernova may have influenced Earth's climate. Some scientists suggest explosions within a few hundred light-years may have triggered ice ages by altering cosmic ray flux and cloud formation. Supernova can be replayed by gravitational lensing. When their light is bent around massive galaxies, astronomers may see the same explosion appear multiple times in the sky, delayed by months or years. Studying supernova in the infrared reveals material hidden by dust. These observations show how much mass is ejected and whether dust formation, essential for planets, begins quickly after the blast. The brightness of a supernova can help estimate the rate of star formation in distant galaxies. More explosions imply more massive stars are being born, offering clues to how galaxies evolve over time. Supernova remnants act as cosmic clocks. By measuring their expansion rates, astronomers can estimate when the explosion occurred, even if it wasn't recorded by humans. SN 1572, recorded by Tycho Brahe, demonstrated that change occurs in the heavens, undermining the ancient Aristotelian belief in unchanging skies. This event helped propel the scientific method into astronomy. Supernova can help locate hidden black holes and neutron stars. By tracing the debris, astronomers can find compact remnants that reveal themselves only through X-rays or gravitational effects. The role of supernova in creating calcium means every bone in our bodies carries the mark of stellar death. Without them, vertebrates would not have skeletons, and life on Earth would look profoundly different. Some supernova occur in star clusters, where many massive stars are born together. The combined energy of multiple explosions can blow away most of the cluster's gas, halting further star formation. The supernova rate in galaxies provides insight into stellar populations. Spirals like the Milky Way produce more explosions than elliptical galaxies, which contain mostly old, low-mass stars unlikely to explode. The collapse of a star's core during a supernova happens in less than a second. This unimaginably fast process determines whether the remnant becomes a neutron star or collapses further into a black hole. Light from a supernova can ionize gas thousands of light-years away, altering the chemistry of regions far removed from the explosion. In this way, a single star can shape its galactic neighborhood. The remnants of ancient supernova have been found in deep-sea sediments on Earth. Isotopes like ions suggest nearby stars exploded a few million years ago, sprinkling radioactive dust onto our planet. Astronomers call some explosions hypernovae, which are even more energetic than standard supernova. These extreme blasts are thought to be linked with gamma-ray bursts, the most powerful electromagnetic events in the universe. The first detection of neutrinos from a supernova came from SN 1987A. In the Large Magellanic Cloud, 3 different observatories picked up a tiny burst of particles, confirming theories of how stellar cores collapse. Supernova are not just destructive, they drive cosmic winds that regulate star formation in galaxies. Without them, galaxies would form stars too quickly and burn through their gas supplies prematurely. SN 1987A gave astronomers the rare opportunity to watch a supernova evolve in real time. Decades later, telescopes still track its expanding shock waves and the birth of new structures within the remnant. Some of the heaviest stars, more than 100 times the mass of the Sun, may undergo parent stability supernova, where gamma rays transform into matter-antimatter pairs, destabilizing the star and blowing it apart completely. With no remnant, the light from a supernova can be scattered by interstellar dust, creating a light echo that continues to illuminate the surroundings years, or even decades after the initial explosion. Supernova remnants often accelerate electrons that spiral around magnetic fields, producing synchrotron radiation, the bright radio waves we detect long after the explosion. In some galaxies, supernova rates are so high that the combined explosions heat entire regions, driving outflows of gas called galactic which shape galaxy evolution. A supernova's shockwave can compress nearby gas clouds, triggering the formation of new stars. Thus, the death of one star may plant the seeds for the birth of many more. The famous star Betelgeuse in Orion is expected to explode as a supernova sometime in the next 100,000 years. When it does, it will likely outshine the moon in Earth's night sky. Some supernova remnants form stunning filaments of glowing gas. These wisps, seen in objects like the Veil Nebula, reveal the chaotic turbulence left behind by a massive explosion. The study of supernova remnants often involves X-ray observatories like Chandra, which can see the million-degree plasmas invisible to optical telescopes. The distribution of supernova remnants across the Milky Way helps map the galaxy's spiral arms. Since massive stars, the ones that explode, fall mostly in those regions, supernova may be linked to mass extinctions on Earth. If one occurred within 30 light, the resulting radiation could damage the ozone layer and expose life to harmful cosmic rays. Supernova contributes to the galaxy's dust content. Though much of it is destroyed in shocks, some survives and eventually becomes part of planets, comets, and even living organisms. SN 1993J in the galaxy M81 was one of the best observed supernova of the 20th century. Its brightness, proximity, and unusual spectrum helped refine the classification of type. IIb supernova. Supernova can even alter galactic chemistry by enriching gas with oxygen, carbon, and iron, changing the metallicity of future stars. The death of massive stars through supernova ensures that galaxies never stagnate. Without them, galaxies would be dominated by hydrogen and helium alone, lacking the diversity of elements needed for rocky planets and life. Some supernova leave behind pulsar neutron stars that beam radio waves in lighthouse-like patterns. These cosmic clocks rotate with astonishing precision, sometimes hundreds of times per second. The shape of supernova remnants is rarely spherical. Instead, asymmetries caused by rotation, magnetic fields, or binary companions give them chaotic, twisted geometries. Type Ia supernova, caused by white dwarfs, are crucial standard candles for cosmology. Their predictable brightness made it possible to discover the accelerating expansion of the universe in the 1990s. Some supernova occur inside dense, circumstellar shells of gas blown out by the star in its dying phases. When the explosion collides with this material, It creates extra bright events called type IINSUPERNOVAE. In the cores of collapsing stars, densities reach beyond atomic nuclei. Matter becomes so compressed that it behaves like a neutron-rich fluid. Unlike anything found naturally on Earth, supernova remnants can stretch across dozens of light-years. Over time, their energy spreads thin, blending back into the interstellar medium as a diffuse enrichment of gas. The bright blue rings, seen in SN 1987A's aftermath, were created by material ejected thousands of years before the explosion. The supernova's blast has since illuminated them in detail. Gamma-ray bursts, some lasting only seconds, are thought to result from certain kinds of supernova. These events outshine the rest of the universe during their brief lifetimes. The amount of energy released in a supernova rivals the Sun's total output over its entire 10 billion-year life. Unleashed in a matter of seconds, 2 days, supernova shockwaves can ignite molecular clouds, potentially setting off chain reactions of star birth that spread across vast regions of a galaxy. Because supernova produce cosmic rays, they may subtly influence Earth's atmosphere by seeding cloud formation, linking stellar death to climate. The Crab Nebula, remnant of SN 1054, is still expanding at about 1,500 kilometers per second, nearly a millennium later. Its pulsar continues to energize the nebula, making it a cosmic beacon. Supernova remnants act as laboratories for studying the behavior of matter under extreme conditions, helping scientists test theories of nuclear and particle physics. The timing and frequency of supernova help scientists understand how long massive stars live. Since only stars above certain masses end in such explosions, some supernova are so massive that their cores collapse directly into black holes. But the violent process still drives shockwaves and outflows that spread heavy elements into space. When light from a supernova is scattered by interstellar dust, it can reach Earth years later. Astronomers studying light echoes can reconstruct spectra of ancient explosions long after the event in dwarf spheroidal galaxies. Even a handful of supernova can strip away most of the gas, halting star formation for billions of years. Type Ia supernova occur in binary systems, but the exact nature of the companion star, whether another white dwarf or a normal star, is still debated. Supernova explosions help to explain the observed abundance of elements across the universe. Without them, our models of cosmic chemistry would not match reality. The study of supernova remnants like Cassiopeia A has revealed jets of material blasting outward in opposite directions, showing that explosions can be highly directional. SN 1885 in the Andromeda Galaxy was the first extragalactic supernova ever observed. Even though it predated modern telescopes, records confirm its brilliance. Supernova help refine models of stellar interiors, because the way they explode reveals details about fusion processes deep inside massive stars. In the Milky Way, the rate of supernova is estimated at 1 or 2 per century. The fact that we haven't seen a bright one since Kepler's in 1604 means we are overdue. Some supernova remnants contain knots and clumps of material, moving at different speeds, suggesting highly irregular explosions rather than smooth detonations. Astronomers detect expanding shells of gas around some white dwarfs on the verge of exploding, hinting at their imminent detonation. As type Ia supernova, the light curve of a supernova, how its brightness changes over time, reveals the physics of the explosion. From nickel decay to interactions with surrounding material, the explosion of a star can alter its entire neighborhood, heating gas, destroying dust grains, and redistributing energy across dozens of light years. Supernova demonstrate cosmic recycling. Stars live, explode, enrich, and die, making possible the next generation of stars and planets. Without supernova, the periodic table would stop at oxygen. Heavier elements like iron, copper, silver, and gold owe their existence to these stellar cataclysms. Astronomers studying supernova remnants in multiple wavelengths, radio, optical, infrared, and X-ray, piece together a complete picture of the violent aftermath. Some supernovae show unusual spectra that defy classification, suggesting new types of stellar deaths waiting to be understood. Theoretical models predict that stars between 140 and 260 solar masses end in parent stability supernova, exploding entirely without leaving a remnant behind. The colors seen in supernova remnants are not just aesthetic, They reveal the chemical composition of different filaments, mapping out what the star was made of. Supernova-driven winds help distribute elements from galaxies into intergalactic space, enriching the vast cosmic web with the seeds of future systems. That the timing of pulsars born in supernova can be so precise that they rival atomic clocks, turning cosmic violence into tools of incredible accuracy. In the distant past, ancient humans may have seen supernova brighten the skies, weaving them into myth and story as mysterious celestial visitors. The collapse of a star's core halts abruptly when neutrons resist further compression. This sudden stop rebounds outward, creating the shockwave that tears the star apart. The brightest supernova ever recorded, SN 1006, was so luminous that it cast shadows on Earth at night and was visible for months. Astronomers sometimes detect delayed detonations in Type Ia supernova, where the explosion starts as a slow burn and transitions into a runaway detonation. The Crab Nebula's pulsar emits beams of energy that continue to accelerate particles, energizing the nebula like a cosmic generator long after the star's death. The heavy elements blasted into space by supernova eventually become part of rocks, oceans, and even the iron in human blood. Supernova are among the rare phenomena where nuclear physics, particle physics, and cosmology converge, making them central to understanding the universe. The iron abundance in stars is often used as a marker of how many supernovae have enriched a galaxy's gas over time. SN 1987A continues to glow decades later, as its shockwave collides with material thrown off before the explosion, providing a unique long-term laboratory. Some supernova remnants reveal high-speed jets shooting outward, suggesting asymmetric explosions linked to rapid stellar rotation because of cosmic time travel. Some supernova we see today actually exploded billions of years ago, long before the Earth had even formed. Astronomers hope the next nearby supernova, when it happens, will be visible to the naked eye and provide unprecedented scientific data with modern instruments. Supernova remind us that stars, though seemingly eternal, have life cycles. Their explosive deaths fuel the renewal of the cosmos in endless cycles of creation and destruction. Some of the most detailed maps of magnetic fields in space come from polarized light emitted by supernova remnants, revealing tangled and amplified field structures. The discovery of superluminous supernova in recent decades has expanded the known range of stellar explosions, some being more than 100 times brighter than typical events. Supernova can reveal hidden populations of stars in galaxies, since they often occur in regions where individual stars cannot otherwise be seen. Even though supernova are rare in any single galaxy, occurring only a few times per century, across the observable universe, astronomers see them nearly every night. The heavy isotope iron-60 found in ocean sediments is evidence of nearby supernova within the last few million years, possibly influencing Earth's environment and evolution. Supernova demonstrate the intimate link between the micro and the macro. Quantum processes in atomic nuclei determine the fate of stars, millions of times more massive than Earth. Astronomers use supernova to probe dark energy, since their observed brightness and distance relationship encodes how the universe's expansion has changed over time. The layered structure of exploding stars leads to different elements being ejected at different speeds. Outer layers travel faster, while iron-rich cores expand more slowly. Supernova remnants in radio waves often reveal large circular shells invisible to optical light, showing how much gas has been displaced. The distribution of supernova remnants near the galactic plane reflects where massive stars are born in dense star regions of spiral arms. Some supernova are preceded by violent stellar eruptions just years before the final blast, as if the star convulses before death. These precursors are a hot topic of study. The shockwave from a supernova can heat gas to tens of millions of degrees, making remnants, strong X-ray sources visible across the galaxy. The famous astronomer Johannes Kepler carefully recorded the supernova of 1604, now known as Kepler's supernova. It was one of the last naked-eye supernovae in the Milky Way. Supernova remind us that stars are not eternal. Their explosive deaths recycle the universe, ensuring that galaxies, planets, and life continue to evolve. The cycle of supernova explosions across cosmic history gradually transformed the universe from simple hydrogen and helium into a place rich with complexity. Astronomers are still trying to determine whether some supernova could produce both a neutron star and a black hole. Depending on how matter falls back after the explosion, supernova are not just astrophysical curiosities, they are the reason planets exist, the reason life has chemistry, and the reason the cosmos evolves beyond simplicity. Not every massive star ends in a visible supernova. Some may collapse quietly into black holes in what astronomers call failed supernova, where the outer layers fall inward and the event produces only a faint flicker. The detection of gravitational waves now opens a new way to study stellar deaths. While merging black holes are the main source, collapsing cores of massive stars may also ripple spacetime during supernova events. Supernova are cosmic engines of change. Without their explosions to stir and enrich interstellar matter, galaxies would stagnate, deprived of the diversity that allows new generations of stars and worlds. In our Milky Way, astronomers estimate there are about 400 known remnants of past supernova, though many more likely remain hidden by dust or have faded too much to detect. SN 1054, which produced the Crab Nebula, was recorded not just in China and the Middle East, but also by Native American cultures, carved into rock art that still survives today. Because supernova shine so brightly, they allow astronomers to peer across billions of light years. Some distant ones are seen as they were when the universe was only a fraction of its current age. Type 2 supernova display hydrogen lines in their spectra, while Type 1 lack hydrogen. This simple division reveals much about the progenitor star and its fate before the explosion. Astronomers can reconstruct the internal structure of a dead star by analyzing the chemical fingerprints in its supernova remnant. Much like dissecting a cosmic autopsy, the immense energy of a supernova can briefly turn a single star into one of the brightest objects in the entire observable universe. Visible across galaxies, the expansion speed of supernova ejecta is staggering, often reaching 20,000 kilometers per second. Entire layers of a star are hurled into space at speeds beyond imagination. Some supernova are linked to binary star systems, where interactions between companions strip layers and influence how the final blast unfolds. Supernova remnants can glow for tens of thousands of years, lighting up the interstellar medium with their shockwaves and providing long-term beacons of past stellar deaths. Astronomers use three-dimensional maps of supernova remnants, built from Doppler shifts and X-ray data, to reconstruct how explosions unfolded in their first moments. Supernova-driven shockwaves may seed magnetic fields in galaxies, amplifying them over cosmic time and shaping the evolution of interstellar space. The name nova originally referred to any new star appearing suddenly. Only later did astronomers distinguish supernova as the vastly more powerful stellar deaths. Supernova also contribute to the enrichment of planetary atmospheres. Even Earth's air contains oxygen and nitrogen made possible by ancient explosions. Some theorists suggest that nearby supernova in Earth's past may have influenced evolutionary leaps by altering climate or exposing life to higher radiation. Because neutrinos escape the collapsing core before light does, a neutrino burst from a future nearby supernova could alert astronomers hours before the explosion becomes visible. The supernova remnant, Cassiopeia, about 11,000 light-years away, exploded around 1680. Its expanding shell glows across the electromagnetic spectrum, from radio to X-rays. Even in their death throes, stars exhibit extraordinary variety. No two supernova are exactly alike, and studying their diversity reveals the complexity of stellar evolution. The deaths of the first stars through supernova created the earliest black holes, which may have merged and grown into the supermassive giants now lurking in galactic centers. Some supernova remnants, when mapped in infrared, reveal cool dust forming from the ashes. This dust becomes part of the raw material for new stars and planets. In a galaxy cluster, the combined effect of thousands of supernova helps regulate gas temperatures, preventing runaway cooling and collapse at the cluster's core. Because Type Ia supernova are so reliable, they serve as one of the key tools for measuring cosmic expansion and estimating the age of the universe. Astronomers sometimes detect supernova imposters, giant eruptions of luminous blue variable stars that mimic explosions but leave the star intact. A supernova explosion in a galaxy can outshine the entire galaxy for weeks, temporarily shifting the cosmic balance of light in the night. Sky. The energy released in neutrinos during a core collapse supernova is staggering, about 99% of the total energy, though only a tiny fraction reaches Earth. In the earliest moments of a supernova, shock breakout occurs, releasing a brief but intense flash of ultraviolet and X-ray light as the shock wave reaches the surface of the star. Supernova remnants are prime sites for studying turbulence, as shock waves stir the interstellar medium into chaotic patterns that influence star formation. Supernova are the universe's way of recycling matter, breaking apart dying stars and scattering the raw elements needed for life across galaxies. Without these titanic blasts, planets, oceans, and even our own bodies could never have formed, because supernova are the cosmic factories that seed space with iron, carbon, and oxygen. When a massive star approaches its end, it fuses elements in its core until it reaches iron, the point of no return. Iron cannot release energy through fusion, so the star collapses under its own gravity. In just seconds, the core rebounds and unleashes an explosion so bright it can outshine an entire galaxy for weeks or months. The light from a supernova can travel millions of years across the cosmos before reaching Earth. Ancient civilizations often recorded these mysterious guest stars suddenly appearing in the night sky, not knowing they were witnessing the death of a sun millions of times larger than their own. One of the most famous recorded supernova occurred in 1054 AD, when Chinese astronomers described a star so bright it was visible even in daylight for nearly a month. Today, the remnant of that explosion is the Crab Nebula, still glowing in the sky as a reminder of that cosmic detonation. Supernova remnants like the Crab Nebula aren't just beautiful, they are also rich laboratories where astronomers can study the aftermath of stellar death. These expanding clouds of gas and dust hold secrets about how elements spread through space, and how new stars are born from recycled material. Single supernova releases more energy in its explosion than our sun will emit over its entire 10 billion year lifetime. For a brief moment, one dying star can release as much light as hundreds of billions of stars combined, reshaping its corner of the galaxy in an instant. There are two primary types of supernova: core collapse and thermonuclear. Core collapse supernova occur when massive stars exhaust their fuel, while thermonuclear supernova happen when white dwarfs in binary systems steal too much material from their companions and ignite runaway nuclear reactions. Thermonuclear supernova, often called Type Ia, are particularly important for astronomy because they all explode with nearly the same brightness. Scientists use them as standard candles to measure cosmic distances, helping us map the universe and discover that it is expanding at an accelerating rate. When a massive star undergoes core collapse, the immense pressure squeezes protons and electrons into neutrons, creating a neutron star. These ultra-dense objects are just a few kilometers wide but contain more mass than our sun, with gravity so intense that a teaspoon of neutron star matter would weigh billions of tons on Earth. Sometimes, if the collapsing star is massive enough, the core's gravity overwhelms even neutron degeneracy pressure, and the result is the birth of a black hole. Thus, supernova not only destroy stars but also give birth to some of the universe's most extreme objects. Astronomers estimate that a supernova occurs about once every 50 years in our Milky Way galaxy. Though rare on human timescales across the billions of galaxies in the observable universe, hundreds explode every single second, each one reshaping its surroundings. The shock waves from supernova compress surrounding clouds of gas, triggering the birth of new stars. In this way, stellar death directly leads to stellar birth, continuing the cosmic cycle and ensuring galaxies remain vibrant and filled with light. Supernova are also thought to play a role in the formation of planetary systems. By scattering heavy elements like silicon, iron, and nickel, they provide the essential ingredients that clump together into rocky planets like Earth. In fact, the iron in our blood and the calcium in our bones were forged in ancient stars and spread across the galaxy by supernova explosions billions of years before our sun was even born. Each of us carries the fingerprints of these cosmic blasts within us. Some supernova are so luminous they are called hypernovae, which occur when extremely massive stars explode with energies many times greater than a typical event. These are rare, but when they happen, they are among the brightest phenomena in the universe. Hypernovae are also linked to gamma-ray bursts, the most powerful explosions known, lasting only seconds or minutes. These bursts release more energy than our Sun will in its entire existence, blasting narrow beams of radiation across space. If a gamma-ray burst were to occur close to Earth, it could strip away our planet's atmosphere and cause mass extinction. Luckily, such events are incredibly rare in our galactic neighborhood, and most point their deadly beams far from us. Supernova can create complex, beautiful shapes in the sky. The glowing remnants often take on intricate structures, with filaments of gas stretching like ghostly webs, sculpted by magnetic fields and the energy of the blast. The study of supernova has revolutionized our understanding of the universe. By observing their light, astronomers have been able to probe the physics of matter under extreme conditions and even measure the presence of mysterious dark energy. In 1987, a supernova erupted in the Large Magellanic Cloud, a neighboring galaxy, known as SN 1987A. It was the closest observed in centuries and gave astronomers unprecedented insights into stellar death, including the detection of neutrinos released in the explosion. SN 1987A confirmed many theories about how supernova worked, but also raised new questions, particularly about the mixing of elements inside the star before it blew apart. Even decades later, it remains one of the most studied stellar events. The remnants of supernova can last for tens of thousands of years, gradually expanding and fading as they enrich their surroundings. Each remnant becomes part of the interstellar medium, a cosmic graveyard that also serves as the cradle for new stars. Some stars, called supernova imposters, mimic the brightness of true explosions but survive the event. These are massive stars undergoing violent outbursts, ejecting layers of material but avoiding total destruction. Now, the brightness of a supernova is so immense that it can sometimes be seen by the naked eye on Earth, even if it happens in distant galaxies millions of light-years away. For ancient sky watchers, these sudden bursts must have seemed like omens from the gods. In the modern era, supernova are tools for measuring time and distance on a cosmic scale. By comparing their light curves and spectra, astronomers can gauge not just where they happened, but also how fast the universe is. Expanding supernova are also linked to rapidly spinning neutron stars that emit beams of radiation. The Crab pulsar, found at the center of the Crab Nebula, spins 30 times per second and still energizes the remnant around it nearly 1,000 years after the original explosion. Astronomers classify supernova into several categories: type I, IB, IC, II, and so on, based on their spectra and the physical processes behind them. Each type provides a different window into the complex lives of stars. Some supernova leave behind no visible remnant at all. The star simply collapses directly into a black hole, its light swallowed forever. Detecting these failed supernova is a challenge, but they may account for many massive stars that disappear mysteriously. Supernova are not just explosions, they are transformations, rewriting the chemistry of galaxies. A star that has spent millions of years forging elements suddenly releases all its treasures in one violent instant, scattering carbon, oxygen, magnesium, and iron into space. These elements drift, cool, and merge into new stars, planets, and even life itself. In this sense, a supernova is not the end of a story, but the prologue to countless new beginnings. The sheer energy unleashed by a supernova is beyond human comprehension. In seconds, it can emit more light than a galaxy of billions of stars. Imagine a single pinprick in the sky that suddenly blazes brighter than everything else combined, in an event so powerful it sends shockwaves rippling through interstellar space, rearranging the cosmic landscape for thousands of light-years. Supernova are also clocks of the universe, marking the passage of time on scales too vast for us to fully imagine. Astronomers can look at remnants, measure how fast they expand, and trace their origins to events that happened centuries or millennia ago. Each glowing cloud is a cosmic diary entry, recording the last words of a dying star. The famous Crab Nebula is one such diary. Born from a supernova observed in 1054, its intricate filaments still shine, powered by a central pulsar. To ancient astronomers, it was a dazzling new star in the sky, but today we know it was the death cry of a massive sun. A transformation so violent it still echoes across space nearly 1,000 years later. Our own Milky Way has experienced many supernova, though not all were recorded. Astronomers estimate that one occurs about every 50 years in our galaxy, but the vast dust clouds of the spiral arms hide many from view. We may be living in a cosmic lull, waiting for the next great burst to light up our skies. Betelgeuse, the red supergiant in Orion, is a prime candidate. Enormous and nearing the end of its life, it will one day collapse and explode in a spectacular supernova, visible even in daylight. Whether that happens tomorrow or 100,000 years from now, the universe already has its fuse lit. Supernova are not silent. While the explosion itself cannot be heard in the vacuum of space, it sends ripples through space-time gravitational waves that we can now detect with advanced observatories. These faint signals are the whispers of stars tearing themselves apart, vibrating the very fabric of the cosmos. When supernova erupt, they release floods of neutrinos, ghostly particles that almost never interact with matter. Billions stream through our bodies every second unnoticed. Yet, during a nearby supernova, detectors on Earth can pick up a surge of these elusive messengers, offering us a glimpse into the star's final moments. SN 1987A, the closest modern supernova, taught us much about this. Its neutrinos were detected hours before the light reached Earth, confirming theories about how the collapse begins deep inside the star's core before the explosion breaks free. It was a once-in-a-lifetime cosmic alert, a window into stellar death. The debris left behind by supernova becomes a laboratory for cosmic chemistry. In these turbulent regions, molecules form under extreme conditions, creating complex compounds that eventually seed new solar systems. The water in Earth's oceans and the carbon in living cells owe their existence to these long-ago fireworks. Not all supernova are the same. Some strip their outer layers before exploding, leaving different chemical signatures in their light. By studying these fingerprints, astronomers can reconstruct the lives of stars, from their first hydrogen fusion to their final collapse. It is stellar forensics on a galactic scale. Type Ia supernova, the result of white dwarfs stealing matter from companions, are especially important because of their uniform brightness. Like cosmic street lamps, they let us measure distances across billions of light. In the 1990s, these standard candles revealed that the universe is not just expanding, but accelerating. Driven by the mysterious force of dark energy itself might never have been discovered without supernova. By comparing how bright distant type Ia events appeared to how bright they should be, astronomers realized something was pushing galaxies apart, faster and faster. Thus, stellar death led to one of the greatest cosmological discoveries of our age. The remnants of supernova are sculptors of galaxies. Their shockwaves compress clouds of gas, triggering the birth of new stars. At the same time, they can blow gas out of galactic regions, regulating star formation. In this way, explosions both nurture and hinder, maintaining balance in galactic ecosystems. Some of the most breathtaking images captured by telescopes are of supernova remnants. Swirling clouds of neon green, crimson, and electric blue stretch across light years, resembling cosmic fireworks frozen in time. These remnants are more than art. They are maps of energy, magnetism, and history painted on the night sky. Supernova are also tied to the most mysterious objects in the cosmos, black holes. When a massive enough star collapses, its gravity overwhelms all resistance, creating a singularity where time and space fold in on themselves. Every black hole began its existence as the heart of a dead star, born in fire and fury. But if the collapsing core doesn't quite reach that point, it stabilizes as a neutron star, one of the strangest entities imaginable. Just 20 kilometers wide, a neutron star can weigh twice as much as the Sun. A single teaspoon of its material would outweigh mountains, crushing everything with gravity billions of times stronger than Earth's. Neutron stars sometimes become pulsars, spinning so fast they flash beams of energy into the cosmos. These cosmic lighthouses are relics of supernova, still rotating long after the star's outer layers were blown away. The Crab pulsar, for instance, continues to spin 30 times per second, its beams sweeping space like a beacon of stellar death. Supernova even affect life on Earth. Scientists have proposed that nearby explosions in the past may have altered our planet's atmosphere, possibly contributing to mass extinctions. The traces of certain isotopes found in ocean sediments hint that Earth has felt the blast of stellar death before. In a way, we owe our existence to such blasts. Without supernova enriching the galaxy, there would be no rocky planets, no oceans, and no humans to wonder about the stars. Every breath we take is made possible by atoms forged in stellar furnaces and flung outward in explosions. That happened billions of years ago. The most extreme kind of supernova occur when titanic stars collapse with unparalleled violence. These rare events can produce jets of energy that erupt at nearly the speed of light, sometimes creating gamma-ray bursts that streak across galaxies like cosmic death rays. Gamma-ray bursts, though lasting only moments, are the most luminous events known. A single burst can emit more energy than our sun will in its lifetime. Astronomers watching them unfold are seeing a story of destruction that is also one of creation. For these events reshape the universe around them. Though terrifying in scale, the vast distances of space protect us. The odds of a gamma-ray burst or supernova happening close enough to threaten Earth are vanishingly small. Instead, we can safely watch these cataclysms from afar, learning from their light without fearing their fury. Supernova also challenge our imagination. To picture one is to envision a star swelling, collapsing, and detonating with more power than humanity has words for. It is both terrifying and beautiful, the ultimate paradox of the cosmos: death that gives life, destruction that plants seeds for the future. Astronomers now use vast sky surveys and robotic telescopes to detect supernova in distant galaxies. Hundreds are discovered each year, each one offering a new puzzle, a new story about how stars live and die. By piecing them together, we write the biography of the universe itself. Even in their silence, supernova speak. Their light curves, spectra, and remnants carry messages across time and space. To read them is to listen to the voices of dead stars, still echoing long after their final breath. And those voices tell us a story as old as the cosmos. Nothing truly ends, it only transforms.